Now we're going to talk a little bit about the properties of determinants or some other things that we can do to find determinants. Squiggly, squiggly. Okay, so first thing, maybe this didn't come to your mind, maybe it did. So we talked in the last video about a triangular matrix. And your brain might have said, well, why don't we go back to that other one and make that the giant matrix that we looked at, why don't we make it triangular? Like, it was pretty close to being triangular. We could have done some row reductions to make it triangular, but are they going to be equivalent? So essentially, we want to know, will row operations have any effect on our determinant? So let's try it out. Let's see what happens here. So first thing I want to do, so here we go. I have the matrix 3, 4, -1, 7, and I want to find its determinant. So the determinant here is equal to, so 3 times 7 is 21, minus, here, we'll make that clear that it looks like a -1, minus a -4 means plus, so I get a determinant of 25. All right, now I'm going to start my row reductions, and I'm going to do these painstakingly slow. Right? So sometimes I will do a couple all at once, and when you're solving and trying to get to the end point and sort of use this to tell us about a system or any of those kind of things, then yes, you may want to do a couple of operations at once. But we're going to do them painstakingly slow right now. So the first thing I'm going to do is I have that 3 in that upper position in the 1, 1 position, but I don't want a 3. I want a 1. So the first thing I'm going to do is I'm going to switch my rows. And this will give me my new matrix, -1, 7, 3, 4. Right? I haven't done anything really complicated. But let's see what happens to the determinant. So this time I have -1 times 4 is -4, minus 3 times 7 is -4 minus 21 gives us a -25. Curious. Those things are not the same. And you probably guessed by now, based on what's next in the notes, that that's probably true. That most of the time, our row operations do not keep our determinant consistent. But is there a pattern here? Let's find out. All right, next thing I'm going to do, I want to change my 1 in the top position. I need that to be a positive. So I'm going to multiply this row, different number, color. I'm going to multiply this by -1, right? Or divide by -1, doesn't matter. And this will give me the new matrix 1, -7, 3, 4. And watch what happens here. So our determinant is equal to 1 times 4 is 4, minus 3 times -7 minus a -21 is a positive plus 21. So 4 plus 21, we're back to 25 again. Keep this in mind. That's going to be key here. Keep that in mind. All right, next thing I'm going to do, I want to get rid of that. So far we've shown 2 different row operations and what happens to the determinant. So now let's do a third type of row operation. We're going to do our replacement. So I'm going to take row 3 and I'm going to subtract 3 row 1. And this is going to give me 1, -7, 0, and 25. Yay. Ooh, that makes our determinant really nice, right? Anytime you have a 0 on either in any position, that makes part of the diagonal nice and easy, so I don't even have to worry about the second half. So my determinant here is also 25. Curious. Very curious. Last but not least, I'm going to do one more just to get us down to just for funsies. The last thing I'm going to do is I'm going to divide this by 25, right, to get it down to a matrix that looks like 1, -7, 0, 1. If I wanted to go even further, I could, but you'll notice the determinant here is 1. Ooh, again, keep that guy in mind. Keep that in mind. So each one of my row operations does have some influence on our determinant, and that's okay. And we're actually going to use these to help us out a little bit. So the first one, a replacement. So anytime, and notice, so a replacement means that row, the row you're replacing you can't multiply that row by anything, otherwise you're scaling. So it either needs to be a row 2 minus something row 1, or row 2 plus something row 3, whatever. We can't have a scalar on the row that we're trying to replace. Hope that makes sense. Right, so it just needs to be row n plus or minus s row other ones, whatever. That's not even helpful. Let's try that again. All right, so a replacement, no change to our determinant. So any replacement we do, again, making sure that the row we're replacing, we're not doing any kind of scaling to that particular row. So as long as we do that, there's going to be no change to our determinant. When we interchange, right? So notice what happened here when I changed the top and the bottom row. My determinant went from a positive 25 to a negative 25, and that's always going to be the case. So when we go, all right. So no change to determinant. That means determinant A here in symbols is determinant B. Right, so we're transforming from one matrix to another. They're equivalent matrices, but it turns out our determinants are not equivalent. When we interchange, they switch signs. That is the determinant of A is equal to the negative determinant of B, or vice versa. The determinant of B, because that's kind of what we're going for, is equal to negative determinant of A. Those are equivalent statements, right? The last one, scaling. So you'll notice when I multiplied by -1, my determinant went from a negative 25 to a positive 25. When I multiplied by 1/25, right, so dividing by 25 is equivalent to multiplying by 1/25. So when I multiplied by 1/25, my determinant also got multiplied by 1/25. So scaling, if I scale by k, that means that my determinant is also going to scale by k. So the determinant of B becomes whatever k times the determinant of A is. Now, again, this k could be a whole number, could be a fraction, could be whatever, right? So if I divide by k, that's equivalent to multiplying by 1 over k. So same idea, right? So how can we use this idea to help us find determinants of really tricky matrices? Well, if we think back to that matrix that we did in the last video that had 8 billion entries, we actually had a lot of zeros in it, right? So it wasn't really as tricky as it needed to be, or it could have been. We had a lot of zeros in it, but it wasn't quite a triangular matrix, right? So if you recall, I can also take, for a triangular matrix, if I just multiply the entries in the diagonal, that is the determinant. And I guess we could have proved that, right? Oh, there we go. Here's the proof, right? The reason that works, there's a 2 by 2 matrix, and this is technically a triangular matrix here. This guy here is a triangular matrix, and you can see that if I just take 1 times 25, I get my determinant, because anything along this direction, I'd have 0 times -7 is just a 0. Same thing here, 1 times 1 determines 1. So if I can get something down to a triangular matrix, we are golden. I don't have to use my cofactors or anything like that. So the first thing we're going to do is we're going to use our row replacements to transform to get A to be a triangular matrix. And then I'm going to find the determinant of that triangular matrix. So I'm going to find determinant That's the product. Product of the main diagonal for the triangular matrix. And the last thing that I'm going to do, now really, really important here, is to keep track of our row replacements. Because if I can keep track of what my row replacements are, I can backtrack and I can find the determinant of the original matrix. So we are going to backtrack using our row replacements and the triangular determinant to get determinant of A. So here we go. Ready? Here's our determinant. Now we could do our cofactor expansion. I could do a cofactor expansion using either this row or this column because at least I have a 0 in there, but I don't feel like doing that. So I'm going to do some row reductions and I'm going to keep track of what I'm doing as I do them. And then I'm going to use the what those row reductions do to a determinant to kind of backtrack. So first thing I'm going to do is I'm going to replace, all right, so I need to see it, to write it, to feel it, to be a part of it, you know, 7, 0. All right, I'm going to, I don't know, doesn't even really matter, but at some point it does. So I'm going to take row 2 and I'm going to add to row 1. And that's going to give us, so we have 1, -4, 2. We get 0, 0, -5, and the bottom stays the same. Haven't done anything to it yet. All right. Now I'm going to take row 3 and I'm going to add row 1. So my new matrix, I have 1, -4, 2, 0, 3, -2, +2. Why do I have a -3? That's -2. That's just outrageous. I screwed the something on that. In my notes, not here. Okay. Where did I? Hold please. My brain just totally malfunctioned. Okay. Right? If I do row 3 plus row 1, I get 0. Oh, that one's a 0, 0, 5, -5. I get 0. 7 minus 4 is 3. 0 plus 2 is +2. Okay. All right. Now what I'm going to do is I'm going to switch these two. And that's going to give me -1. No. Oh, guys, losing it. 1, -4, 2, 0, 3, 2, 0, 0, -5. Now I don't need to keep going because this is a triangular matrix. It does not matter that I don't have 1s in my pivot positions. We don't actually care. We don't care about that. All we care about is getting down to a triangular matrix and doing some multiplication. So here we go. You ready? So I'm going to take those numbers here. So the determinant of this guy is equal to 1 times 3 times -5, which is -15. And now I'm going to backtrack. So that means if I go back here, so to go from to going forward, I did a switch or an interchange, which means that my determinant switched signs. So this one has a determinant of +15, right? So my sign switched. So this was an interchange, right? Back the next step, so from here to here, I did a replacement, so no change. So our determinant here was 15. From here to here, again, I did another replacement. And you'll notice here each time I did that replacement, the row I was replacing had no multiplier on it. Because if you added a multiplier in that case, what you're doing is doing both a scaling operation and a row replacement at the same time. Not what we want to do. So we did a replacement, which means that the determinant here is 15. So that tells us that our determinant of A is 15, right? Now, as you start to get better and better at this whole idea of row replacements, that was pretty fast to get to a triangular matrix, right? And as long as you pay attention, I don't know about you, but that may or may not have been faster than trying to do our cofactor expansion. Words are hard. Okay. Yeah, just a tickle and a hair left. Not even that late at night yet. So we have 3 theorems here that are going to tell us a little bit more about our determinant. The first one we've seen, right? The first one says that a square matrix is invertible if and only if the determinant's not equal to 0. We know that for a 2 by 2 matrix, also true for a 3 by 3, 4 by 4, it doesn't matter. So it doesn't matter the size. To determine if it is invertible, I need to determine what the determinant is. If it's 0, it's not invertible, and so on and so forth. So either I can say that it's invertible, so I know that the determinant's not going to be equal to 0, or I can say the determinant's not equal to 0, so I know it's invertible. That's that if and only if part. Means I can go forwards and backwards. This one, if A is an M by M matrix, then the determinant of A transpose is equal to the determinant of A. Real quick, you ready? If A is, I don't know, 1, 0, 9, 8, it's a triangular matrix, so my determinant here is 8. Even if I switch those rows and those columns, so this is A transpose is when I switch them, so I have 1, 0, and 9, 8. The only thing that's changed is these guys have switched positions there, which means that my determinant here is still 8. So as long as, if you can find the determinant of A, you can find the determinant of transpose with ease. The last one says if A and B are invertible matrices, if I can find the determinant of the product of the matrices is equal to the product of the determinants of the matrices. That's a mouthful. Say it 3 times fast. Okay. So let's show that that's true. Here's my A, here's my B. First thing I need to find is AB, right? So AB, I'm going to take this column, this row, 6 times, I just flip that again. This row by this column, 6 times 4 is 24, plus 1 is 25. This is a terrible green. I really need to set my presets a little better here. 25. Okay, 25. Now we go this column, this, damn it, I did it again. This row, this column. 6 times 3 is 18, plus 2 is 20. 3 times 4 gives me 12, plus 2 is 14, and 3 times 3 is 9, 2 times 2 is 4, 3 plus 4, 9 plus 4 is 13. Oh, yeah. And now we find some determinants. All right, so the determinant of AB is equal to 25 times 13 minus 14 times 20. I'm gonna save you the heartache. Or, you know, you try it your own. 325 minus 280 comes out to a beautiful 45. Yay! Okay, let's find some other determinants. What's the determinant of A? Well, 6 times 2. Probably help if we could see what the numbers are. 6 times 2 minus 3 times 1 is a lovely 9. Determinant of B is 4 times 2 minus 3 times 1 gives me 5. Unless you don't know how numbers work, and then it's 7. Ask me how I know. So is 9 times 5 equal to 45? Yes! So this is true. Yay! Hopefully, okay, that's it.